Chapter 4, Section 11, Missing Data Imputation, Part 5, Multiple Imputation. In the previous sections, I introduced simple imputation, KNN imputation, and regression imputation. In this section, I will introduce a more advanced method, multiple imputation. It considers and deals with the uncertainty associated with imputing missing data with representative or estimated values. Multiple imputation is an imputation method that considers the uncertainty of missing data. By uncertainty regarding missing data, I mean that when missing values are in a dataset, it is uncertain what the actual values of these missing values are. It is clear that imputation using the mean or median is merely imputation using representative values, and that the actual values are probably different. Also, the estimation of missing data using KNN or regression methods is only an estimation, and it is not possible to identify the actual value. Therefore, there will be an error or a variation in the estimated value of the missing data. This is what we call the uncertainty regarding missing data. The multiple imputation is a method that takes this uncertainty into account. The imputation methods we have looked at produce only a single estimate for each missing data point. These estimates often differ from actual values. However, these imputation methods do not consider this uncertainty. For example, in the case of mean and KNN imputation, only a single imputed value is provided, so these methods ignore the reliability and variation of the results. Multiple imputation is a method for taking this uncertainty into account. Multiple imputation generates multiple estimates for a single missing data point, with each estimate being generated with a random variation, and multiple datasets are created using each estimate. After that, multiple estimation models are created using these datasets, and the results obtained from these models are averaged. This procedure enables us to obtain estimates that reflect the uncertainty of the estimates for the missing data. From a practical perspective, if only one variable contains missing data, the benefits of multiple imputations are not very significant. The first reason is that the impact of missing data is small. If only one variable contains missing data, the impact of that missing data on the overall analysis results may be very small. Therefore, in many cases, a simple imputation method may be sufficient, as the effect of reflecting the uncertainty of missing data is not that great for the whole. The second reason is small return on effort. Multiple imputation requires generating multiple imputed datasets, analyzing each one, and then integrating the results. If there is only one variable that contains missing data, there is a little benefit in going to such trouble, and in many cases, simpler imputation methods will produce sufficient results. However, there are situations where the multiple imputation method is still meaningful even if only one variable has missing data. The first is when important variables contain missing data. For example, if data is missing in the main predictor or outcome variables, that single piece of data could significantly impact the results. In such cases, it is effective to use multiple imputation method to reflect uncertainty and produce more reliable estimates. The second is when the results significantly impact decision-making. When the results of data analysis are related to important decisions such as in healthcare or policymaking, it is necessary to consider the uncertainty associated with the missing data, even if only one variable has missing data. In such cases, it is desirable to make more careful decisions by considering the estimate's variability and uncertainty using multiple imputations. We should perform multiple imputation following these steps. In step 1, determine a single value to impute each missing data. In step 2, generate multiple imputed values based on the single imputed value. In step 3, create multiple datasets using those multiple imputed values. In step 4, perform analysis for each dataset. In step 5, average the analysis results. In step 6, integrate the uncertainty associated with the missing data imputation. In the following, I will explain each step in detail. First, we perform initial imputation to generate a single estimate for rows with missing data. Initial imputation is often carried out using relatively simple methods such as mean imputation and KNN imputation. At this stage, each missing value is imputed with a single estimate, and the entire dataset is converted into a single complete dataset. The purpose of initial imputation is to set a tentative value and use it in the next stage of stochastic imputation. It is important to note that these initially imputed values will not be used as the final values. Next, based on the initial imputation, generate multiple candidate values for the missing values using methods such as MCMC, Markov-Chain Monte Carlo. At this stage, the key is adding randomness and uncertainty so that analysis using different candidate values produce slightly different results. The following processes are carried out at this stage. First, random variation is added to the initial imputed estimates based on the distribution of the data. This means that the imputed data will have multiple variations. For example, suppose the missing data for satisfaction was initially imputed with the value of 3. In this case, random variation following a normal distribution is added to the data, generating various values such as 2.8 or 3.2. Next, we create multiple imputed datasets using the randomness of the imputed values. In most cases, we create 3 to 5 datasets. In the case of 3 different imputed values are generated for the missing satisfaction values, and 3 datasets are created, each containing a different imputed value. This iterative stochastic imputation creates different datasets that reflect the uncertainty of the missing data. This enables us to incorporate randomness and uncertainty that are not considered in the single imputation method, and thus we can perform more reliable analysis. Next, perform the same statistical analysis separately on each of the multiple imputed datasets created in the previous step. For example, we can perform regression analysis with motivation and stress as independent variables, and satisfaction as the dependent variable. We perform regression analysis on each of 3 datasets. Then, calculate the regression equation for each dataset, p-value, MAE, MSE, etc. Calculating the regression equation means calculating each variable's intercept and regression coefficients. The p-value is a value that indicates whether or not each variable has a statistically significant effect. It is calculated for each variable. The MAE and MSE are indicators that quantify the error between the estimated values produced by the regression equation and the actual values of the dependent variable. They are calculated for the entire regression model. It is expected that there will be some differences between these values for the three datasets. In this step, the analysis results from the multiple imputed datasets are pooled to derive final conclusions and estimates. This process enables us to obtain more reliable estimates reflecting the uncertainty of the missing data. Let's take a look at the specific process. In the previous step, we perform regression analysis for three datasets and obtain the parameters and metrics of each regression model. Since the imputed values for missing data differ for each imputed dataset, the values of these parameters and metrics may also differ slightly. In this step, we integrate these multiple analysis results. Specifically, we will average the analysis results. For example, let's average the regression coefficients. Suppose we obtain these results for each dataset. When these values are averaged, the average value of the regression coefficient for motivation is approximately 0.52, and the average value of the regression coefficient for stress is approximately minus 0.22. This is the final integrated regression coefficient. Next, we pool the uncertainty. This is a process of combining the variability of the estimates across multiple imputed datasets. Here, estimates means those of a regression model's parameters such as regression coefficient and intercept. In this step, we do not simply take the mean of the regression coefficients, but rather, we adjust the standard errors to consider the variability of the estimates in each imputed dataset. This ensures that the final analysis results appropriately reflect the uncertainty associated with the missing data. Since each imputation result is slightly different, pooling their uncertainties is an important step to improve the reliability of the analysis. The calculation and combination of variances are performed using a standard method called Rubin's rules. Rubin's rules aggregate the estimates and their variances from multiple imputed datasets to calculate the standard error that considers the uncertainty caused by missing data. I will explain Rubin's rule in more detail later. After averaging the regression coefficients and aggregating the variances across all datasets, we obtain this final regression equation. By using this pooled regression equation to generate predictions, we can make reliable final estimates that incorporate the uncertainty caused by the missing data. In the next section, we will see how to implement these processes by Python. Thank you for watching. Please thumbs up and subscribe to my channel.